Let's go ahead and move on to section 4.3. So in section 4.3, we're talking about measures of variation. And remember, remember that variation measures the spread of the data. So it's letting us know how far away from the center the data all lies. And there's a couple different ways that we can measure variation. Let's go ahead and start by talking about the range. And this is a term that you might have heard before. It's usually covered with median, mode, and mean. So if we're talking about the range of a data set, we're looking for the difference between the highest and the lowest value. So highest value minus lowest value. Or in other words, the maximum of a data set minus the minimum. The range isn't usually often used to describe data just because it can often be misleading. So for example, if we're talking about a data set that has the values 1, 1, 1, 1, and 2, we would say that the range here is 1. But what if I had something where it was, for example, 1, 2, 2, 2, 2. We still have the same range value. Actually, let me try a different example here. 1, 1, 2, 2, 2, for example. So we still have the same range value, but we can see that we do have a little bit different of a variation in our data set than we do in that first one. So before we would say that we could almost consider 2 to be an outlier, since most of those values were 1. Here we can see that the data values are actually more evenly spread out between the two different data values, 1 and 2. So we have the same range, but it's giving us different pieces of information. Let me go ahead and clear the screen just to make a little bit more room for quartiles, just because it does take up a significant amount of space. So moving on to quartiles, which goes hand in hand with something called the 5-number summary. And then also a box plot. So all of these are tied together. Box plot can also be called box and whiskers plot. So if we are looking for the quartiles of a data set, what we're looking to do is we're looking to divide the data set. So it divides the data set into 4 equal size sets. Think of it just the same as like quarter in terms of a dollar. Each quarter is worth 1/4 of that dollar. Same thing here. So if we have a quartile of a data set, each quartile has 1/4 of the data. If we're talking about a 5-number summary, we have to find our quartiles. So we would look for the minimum of the data set, the maximum of the data set. Right in the middle, we're going to have the median. This can also be considered Q2. So the reason why it's Q2 is because notice if I have a data set, if I wanted to divide it into 2 pieces, I would only need 1 line in the middle to divide that into 2 pieces. If I'm looking to divide it into 4 pieces, what I'm doing now is I'm dividing each of those halves in half again. So I would have a quartile 1, quartile 2, and quartile 3 value. And that's what's separating it into the 4 pieces. So I have minimum, quartile 1, quartile 2, quartile 3, and the max. And we do work with some examples a little bit more. I talk through some examples once we get to the practice problems. We end up having a data set that talks about cookies. And then we go in to say, well, let's look for that 5-number summary of each. But we're looking for that 5-number summary. So we have, again, the minimum, which would be over here. Our quartile 1 value, quartile 2, which is that overall median. Quartile 3, and then the max. If we are designating our 5-number summary, we do need to make sure that we're labeling. So either label vertically and say our min is some number, our Q1 is some number, Q2, Q3, and max. Or if we're gonna keep it horizontally, we have to make sure that our numbers are in this specific order. So I should be able to see minimum, Q1, Q2, Q3, and max. I know it's a little sloppy up here, it's just hard to write with these, with a pen. So hopefully you're following along on the completed notes that I have for you. I'm gonna change my color here to talk about a box plot. So if we're talking about a box plot, what we're doing is we are plotting that 5-number summary. So we have to make sure that we first have a number line that covers all of the values that we're going to be discussing in that 5-number summary. Like any number line, we need to make sure that we have this evenly distributed, or the intervals are even. So I'm going to just come up with some hypothetical numbers here. Let's say 5, 10, 15, 20, 25, 30, and 35. And then I'm going to switch to brown here to show how our box plot would come into play. So what we're doing is we want to make sure that we have a line designated for our min. So let's say that our minimum of the data set is 5. In our maximum, and again, I'm just using hypothetical numbers here, is 35. So I have a line drawn for our min, our max, and then also for our quartile values. So let's say that it's 10, 13, 20 as our quartiles. I'm going to go in and draw a line for those values as well. So notice I'm not drawing it on top of the number line, I'm drawing it above it. So that way I can really see where these values are lying. So the minimum and the maximum, I'm now going to do Q1, Q2 at 13, and Q3 at 20. So right now we just have lines, but we need to have a box. So the box is going to be formed by our quartiles. So notice I have Q1, Q2, and Q3 forming my box. And the whiskers are going to be from the box out to the minimum and the maximum. So imagine our cute little stat cat here. Right, so that's our little cute kitty. We have our box representing the quartiles, the minimum, and the maximum are our whiskers. Let me clear the screen to move on to percentiles. So remember that quartiles divided the data set into 4 portions. We're talking about a percentile. We are dividing it into 100 portions. And just as before, when we had in our quartiles, we said, well, I have the min, I have a max, but if I was dividing it into 4 positions, I only had Q1, Q2, and Q3. So notice that there really was no quartile 4 value. The same thing is the case here for percentiles. So the highest that we can have as far as a percentile is the 99th percentile. We'll never see anything that is 100th percentile. And I'll explain a little bit more in just a second. Let me change my color here. So what a percentile represents is, for example, if we're talking about that 99th percentile, we would say that a value at the 99th percentile is greater than or equal to 99% of the data. So notice that I can't have 100th percentile because I can't say that I'm above 100% of the data. I can't be above all of it and then also be a portion of it. So the highest we have there is 99th percentile. Let me erase this right side here because there's going to be 2 computations that we end up doing with percentiles. So when we're talking about a percentile, it could be the case that we are wanting to determine the percentile of a data value. In this case, what we're wanting to do is we need to make sure that our data is sorted. And we need to say, okay, well, how many are below our value? So the number of values lower than the value we're talking about out of the total number of values. And we multiply this by 100 because that is going to be what gives us a percentile. But note here that this is not times 100%. So there is a difference. Percent does not equal percentile. We could also be asked to find the data value at a certain percentile. Notice it's percent, and then I have ILE to be percentile. So what we're looking for here is, let's say that we have a given data set and we want to find what value represents the 35th percentile, or what value represents the 70th percentile. So we're looking to take the percentile in decimal form and multiply it by the number of data values in the data set. The result that we get here is going to tell us what number in the set is at the percentile that we want. And we will work with that a little bit more as we go into the practice problems. I want to talk about one other measure of variation before moving on to section 4.4 and then working through the practice problems with you. So the last measure of variation that we're going to work with here is called standard deviation. As far as measures of variation are concerned, this is the most common single value that is used to describe the variation of a data set. And what this does is this measures how wide the data values are spread out around the mean. So how wide the values are spread out away from the mean. You'll notice that if you look in your book, it gives you a very complex way to calculate the standard deviation. I will not have you actually calculate that by hand. So you will not have to calculate it the way that it shows you in the book, but you will have to be able to estimate. And that's going to be using something called the range rule of thumb, which I'll talk about. And you will also have to be able to interpret. So let's say, for example, I give you a standard deviation or give you two different standard deviations. I might ask which data set is more variant from the mean, or what does it mean to have a low standard deviation? So you'll be asked interpretation type questions. So it is important to understand the concept of a standard deviation, but I don't think that it's necessary for this course to be able to go through and calculate it by hand. So the range rule of thumb is going to be the way to best estimate. And what we're doing here is we can say that the standard deviation is approximately equal to the range of the data set divided by 4. So if we have the data set, we can determine the range divided by 4 and say, okay, this is the best estimate for now that we have as far as the standard deviation for this data set. If we are given a standard deviation, but we don't have any other information regarding our data set, and we want to be able to say, okay, well, what then is possibly our highest value, or what is our lowest value? We can say that the low value, so this is based off of this range rule of thumb, we can say that the low value is about the mean of the data sets. We're going to say whatever is the average, right? So the mean of the data set minus 2 times the standard deviation. And then the high value in the data set is about the mean plus 2 times, or plus, yeah, 2 times the standard deviation. So if we're given The standard deviation and the mean, we could say approximately, this is where most of the data is between. It's going to be between our low value and our high value. And again, we will work more with that as we move on. I'm going to go ahead and erase this and scroll down to 4.4, which is very quick as far as notes are concerned, but I do recommend reading over that section in the book. It talks a lot about mysteries that can happen in statistics. So for example, we can have what is called Simpson's paradox. And Simpson's paradox occurs when the data gives different results. If we look at it in categories, categorical data gives different results than if we look at it all together. And I do have an example that I'm going to work out with you once we get to the practice problems. And then two other things that can happen as well are scenarios called false negatives and false positives. And just the name of these paradoxes is pretty explanatory as far as what's happening in this particular scenario. But if we're looking at a false negative, then let's give it some context here. So we're going to talk about it in terms of cancer, for example. So a false negative is going to be when the test tells us that we do not have cancer, but since that negative is false, what that means is that we do actually have it. So just because the test didn't find it, we cannot say that we do not have it in this instance. We have a false negative. And on the contrary, if we have a false positive, the test says, yes, we have it, but we do not. So we have a false positive. I'm going to go ahead and end this video here and then have the next one pick up working through some practice problems with you.